In this lecture, we're going to talk about isothermal continuous stirred tank reactors. We're mostly going to talk about the steady state design of these reactors. These are very popular in industry, very commonly used reactors because they are cheap, they are easy to maintain, they're easy to operate, and they're also very easy to model. The basic idea is that you have a canister with usually a liquid, but it could be a gas phase inside there as well. It's well stirred in the interior contents, and you have an inlet stream carrying reactants in and an outlet stream carrying products out. Now, because this thing is well stirred, the stream leaving the reactor is going to always be the same concentration as the internal contents of the reactor. And so now you can go through and you can fill in the terms in your generic species balance equation. In fact, all of them are present here if this thing is not at steady state. We have an accumulation term on the left. We have a flow in of species I minus a flow out of species I. And we have a generation rate of species I. So what we're going to do next is to write the inlet and outlet flows in terms of concentrations and volumetric flow rates. This is often a useful thing to do. So these are going to be, the inlet flow rate is going to be the concentration in the inlet stream multiplied by the volumetric flow rate of the inlet stream. And then we have the outlet flow rate is the concentration of the internal contents of the CSTR, species I, multiplied by the volumetric flow rate of the stream leaving the CSTR. Now, if it's a liquid phase, usually you can equate Q and Q naught to each other. There's usually negligible volume expansion in these kinds of reactors and processes. But for gas phase reactions, sometimes those two are different. The residence time is V over Q, just like we used for our previous analysis of plug flow reactors. Let's go ahead and do an example calculation so we can get an idea of how to work with the design equation and make predictions about conversion, volume, residence time, flow rates, and rate constants. Okay, so we're going to do the simplest case here. First, we have a liquid phase reaction where A goes to products. The rate law is first order in A, so some constant times the concentration of A. The volumetric flow rate is going to be Q, and the CSTR volume is V. And we're supposed to go through and find the conversion at steady state. So if you write down our steady state species balance equation for the CSTR, we have 0, no accumulation. We have flow in. We have flow out. So this is the concentration of A in the outlet stream. We have a rate constant times the concentration of A in that outlet stream. Actually, the concentration of A inside the reactor is the same, multiplied by the volume. Okay, so now we go through and we simplify terms here. Notice that this whole thing over here simplifies to Q A naught times X. That typically happens in these calculations. And then if I move things around, I've skipped a couple of steps of algebra. Pause the video and work this out on your own if you like. But what's going to happen here is that all the A naught terms are going to drop out. I can group all the constants together into a KV over Q. That corresponds to K times tau. And all of the X terms grouped together give me X over 1 minus X. So I go ahead now and I solve for X, and I get K tau over 1 plus K tau. The conversion that you reach for a first order reaction in a CSTR is just the rate constant times the residence time over 1 plus the rate constant times the residence time. Now that number, the rate constant multiplied by the residence time, is a dimensionless number. It's known as the Damkohler number. And it's really important. So there are lots of different Damkohler numbers. When we change the reactor configuration, when we change the kind of process that we're looking at, when we change the type of reaction that's happening in that reactor, we typically end up with a very different expression for the Damkohler number in each case. So the common feature in all Damkohler numbers is that they are a non-dimensionalized rate constant, and they usually involve either a flow or a transport of some species in or out of the reaction region. So for a first order reaction in a CSTR, the Damkohler number has this very simple form, and it tells you immediately what the conversion is in the high and low Damkohler number limit. When the Damkohler number is much, much less than 1, then the conversion is approximately equal to the Damkohler number. So a very small number itself. When the Damkohler number is much, much greater than 1, then the conversion is going to approach 1. We can qualitatively understand that by seeing that When tau is extremely large, this reaction has all the time that it wants to go to completion, and the conversion will go to 100%. When the Damn-Kohler number is small, it means that the residence time is much smaller than the reaction time, and so conversion doesn't rise very far. Okay, let's do another example. It's a very similar calculation, but this time we have a liquid phase reaction. A plus B goes to products at 20 degrees C. We're going to hit a targeted conversion, 40%, at steady state operation. The reaction is going to be pseudo first order with respect to A because we're going to have excess B. Therefore, we can think of our rate law as K times the concentration of A, and we're given the rate constant. What we're going to do now is take the volumetric flow rate to be a known quantity, 1.8 meters cubed per hour, and the inlet molar flow rates of A and B are these numbers FA naught and FB naught. Now, it's going to turn out that we don't actually need those. So what we're going to do then is to determine the reactor volume, and we're going to assume that for safety reasons, we're required to operate at 75% capacity. Okay, so again, we plug in everything. First, we're going to find the reactor volume that's actually being used, V. Okay, this is my accumulation of species I, is the flow rate in of species I minus the flow out of species I, the rate of generation of species I. If we do that for species A, then we get 0 is equal to the flow in of A minus the flow out of species A minus K times the concentration of A times V. This is all exactly so far like what we worked before. So now we can go through and we can simplify, solve for V. V is going to be Q divided by K times X over 1 minus X. And that comes out to be, so we have to plug in all these numbers, right? So we had the 1.8 meters cubed per hour, 0.0257 per hour is my rate constant, and my X was 0.4. You plug in those numbers and you get 46.7 meters cubed. We need this thing to operate at 75% capacity, and that means that the volume that we use is 0.75 times the volume of the reactor with the extra space. This is the number that we're supposed to actually find. That volume of the reactor with extra space built in is 62.3 meters cubed.